when crashes are so rare, they could have one-day training seminars about it. Now they're in a different place, obviously. I wrote a second book with a certified Boeing Airbus pilot. He's allowed to write books about airplane crashes, but his company's name doesn't want anything to do with it. My book is based on the most interesting stories I could find, where my presentation is based on the most interesting graphics I can prevent. So a lightning strike for big planes is very common. They get struck about once a year, but it's a totally non-event, a solved engineering problem. They had to resolve the problem for the composite 787, and it's still a problem for small planes without weather radar. They'll get lost and wandered into a thunderstorm. A thunderstorm will structurally destroy any plane. They're simply not designed for that, but it hasn't happened to a big jet in the modern jet era since would be like the early 60s. One of the most common problems is arcing in the fuel vapor space, which could be as simple as a loose rivet. And the tire's on fire there. It's completely safe to be sitting on the inside. The electrons all repel themselves and go to the outer surface, so a human could touch a surface on the inside, although I'm not sure there's any exposed metal surfaces. Everything's covered with plastics. And this is just another pretty picture, although I'll relate one accident that's connected to it. A DC-9 in 1972 was flipped over and crashed, flying too close to a DC-10. And it's most definitely a problem for small planes. I found a couple examples of small planes being broken up in flight, getting too close to a big plane. And it sets the throughput on busy airports. They can simply only fly so close together. So these are little mini tornadoes up to 200 miles an hour. The higher pressure air underneath the wing curls up in the lower pressure on top and creates these two mini tornadoes coming off the wingtips. One of the first things I like to explain is just how survivable an airplane crash is. There are 446 DC-10s made. 27 were destroyed in crashes, but only 4 had total loss of life. A terrorist bomb, 1 flew in the mountain, and just 2 mechanical failures that were clearly engineering issues. And the remaining 23 are planes destroyed in crashes, which means it's essentially like a car being totaled in an accident. It's beyond its economic repair price. Of the remaining 23, even if it's broken into 2 or 3 sections, 85% of the time, 90% of the passengers survive. So the instructions they give you actually are important and can save your life. Everyone assumes everyone dies, so that's simply not the most common case. You can always impact hard enough to kill everyone. It's just usually not what's happening. Usually it's a bad landing or a takeoff where they're closer to the ground at lower speeds. This is a made-for-TV crash. Looks like a seat's being released. So that was an obsolete 727. The pilots ejected before the crash landing. I think it was the Discovery Channel did that. And obviously, if you're near the brake, you can whipsaw it pretty badly. And if your seat is released, it's like being in an accident without a seat belt on. But it's most definitely a survivable crash. And I like to point out this one afterwards. This one obviously hit harder because there's 2 fuselage breaks and only 2 fatalities. Which brings me to this miracle crash of a wide-body L-1011 in the Everglades in 1972. Usually when a plane crashes, you can go to the crash site and point your finger and say, there's the airplane. You'll either see a fuselage or maybe it's broken into 2 or 3 pieces. In this case, there's a debris field, no recognizable cross-section. and it's judged non-survivable, which is an important determination. If it's judged survivable, it triggers a big study of everything, an engineering study of how the structure performed to protect the people, as well as how all the what the flight crew did. So there's nothing to be learned by studying a plane this fragmented. It was judged non-survivable. Only problem is they had 77 actually survive. No one really knows why, no one cares. It's too fantastical to make any sense out of. And this brings me to the most severe, mostly survivable accident that I'm aware of. I've been studying these crashes for a number of years now. DC-10, it had a major uncontained failure of the tail section, and it ripped through all 3 hydraulic lines. You only need 1 hydraulic actuator on each of the control surfaces. So each hydraulic actuator has a hydraulic line plus a backup hydraulic line. And there's 3 of them for redundancy. So if 2 of them break, you still have all the flight surfaces working where the 3rd good one goes to, which is roughly 1/3 or 1/2 of the flight surfaces. So the plane is considered flyable with 2 broken hydraulic systems and half the flight surfaces not responding. And pilots actually practice that scenario in the simulator. Now, the 3 lines are separated widely on the plane for this very reason. So one event cannot take them out, but because of all the hydraulic actuators and the elevators and the rudders and the tail section, it's the only place on the plane where all 3 of them are pretty close together. So a 100-pound piece of engine comes tearing out and wipes out all the hydraulics. They had very limited partial control by varying the thrust of the 2 engines. And we have a crash video. So the plane broke into 3 pieces before bursting into a fireball. Here you see it cartwheeling. So there's the 3 pieces. This is the cockpit section. It was so badly damaged, they just assumed everyone was dead and didn't even go near it for 20, 25 minutes. It turns out that all the flight crew did in fact survive. So roughly 2/3 of the 296 people survived. 75% survived the impact, 2/3 survived the impact and fire, including a baby placed on the floor as instructed, which is still the procedure. They finally invented a baby seat, but it's not required because parents would have to buy an extra seat. FAA studied that and decided parents would be less likely to fly and they'd be more likely to die in highway accidents. So they still don't require buying a baby seat, and you'd still be required to place the baby on the floor in a crash scenario. Here's the ground scar. And here's the recovered broken engine. So this piece went flying out. It's roughly 3 million pounds of centrifugal force when this thing's rotating at 3,600 RPM. So 1/3 of it was like F equals MA with 1 million pounds on 100 pounds of force. And I'm actually the proud owner of such a piece. It's 1960s technology. It's worth more as a donation than an actual engine part. It's like 360 pounds of aerospace grade titanium, about $1,000 a pound retail. There's a rather fierce competition between General Electric and Boeing, or Pratt & Whitney. That was actually sent to me by a GE engineer. So let's take a look at a digital modern 777 and an analog DC-10. With increased computerization, there's more sensors and more oversight. And the whole point of digitizing all that analog information is to shove it in a computer so it could be manipulated. So planes are definitely getting safer and safer, but sometimes the computer confuses things. We'll look at a couple of those examples. So here's your 777 with a bunch of computer screens, and here's the DC-10 with all the analog gauges. So all the information's on the computer screens, and obviously a lot more because you have a lot more sensors. Every generation of plane comes out with more sensors and more complicated software, which is one of the reasons I'm not crazy about talking about the 737 MAX. It's all proprietary software issues and piloting. So we look at the safety of the 777 at DC-10. There's been only 5 hull loss accidents with the DC-10. Surprisingly, you have a reasonable, just a 2/3 reduction in fatalities, but that's not really a fair comparison because one of those is the missing plane with a total loss of life, and another one was struck by a missile. So those are certainly hazards of flying, but hey, we're engineers. There weren't engineering problems. If you delete the criminal acts, there were 2 crashes that killed just 3 people. And of those 3 that died, 2 of them died because they didn't have their seatbelt on during landing. And the 3rd one was indeterminate. It might have possibly survived with a seatbelt on. So here's an example where the computer added to the confusion. And this is the case where the seatbelts I just mentioned. So this unique flight, the pilot was flying a 777 for the very first time. He's a very experienced Airbus pilot, but this is his first training flight on a Boeing 777. And his instructor had like 13,000 hours in a Boeing 777, but his very first flight as an instructor. And it turns out much of the automatic landing systems at the airport were shut off, and the pilot had to fly it more than a normal landing. And basically they got confused by the computer settings and didn't realize the auto throttle was not on, so it crashed on landing. And here's a rather unique case. An Airbus 330 leaves Toronto, August 2001, bound for Portugal, and it runs out of fuel halfway over the Atlantic and glides 75 miles to a safe landing in an emergency abandoned military runway in the Azores. They were very fortunate to find a landing strip where they did, although if a plane goes in the water under pilot control, that's most definitely a survivable event. Hasn't happened for decades now. Usually the ones in the news, they're totally fragmented upon severe impact with the ocean. But if the pilot has control, people are expected to survive. In fact, the slides double as rafts. But anyhow, this is an example where the computers perhaps added to the confusion. So they lost all power because they ran out of fuel. And there is an emergency wind turbine to provide enough power to so you can control the flight surfaces. So you can do a controlled glide. And you can barely see it over there. And what happened was there is a leak. And there's a shell and tube heat exchanger between the engine lubricating oil and the fuel. The oil heats up and it needs to be cooled. So that's done with the fuel flow. And because of the leak, there was more cold fuel flowing through the heat exchanger, which chilled the oil, which is the first odd indicator the flight crew got. Lubricating oil colder than normal, which is not exactly a direct indication of anything. Although my co-author on the second book, he said, as an older pilot, they learned more about flight systems, and they were taught to think engine leak or fuel leak if you have low lubricating oil. And now with all the computerizations, most of the training is how to flip through the computer screens. So they all cool from 230 degrees to 149 degrees, and that puzzled them. They called home for help. So the airline had engineers on standby to address things like this. And the engineers didn't know, they were confused too, which in my mind is a total engineering failure in the sense that if you had something so common, it used to be taught to pilots, why the heck can't the engineers keep track of these oddball, unexpected things? That's the whole point of engineering backup. I guess I said all that. So what happened was this engine was in storage. And for like a year and a half. And since over that time, they redesigned the hydraulic pump. And so there's a new hydraulic pump and a couple of new connecting hoses and tubes. So they changed out the engine in the middle of the night and didn't access the updated documentation. In fact, they talked to the engine manufacturer on the phone and he offered to come in. They said, no, we don't need you. So basically they mixed and matched new and old hoses and tubes. And when it got pressurized and expanded a bit, there was a vibration rub that eventually leaked. And I forgot to mention, pilots actually made it worse. They didn't follow the procedure, so they ended up, well, there's a fuel imbalance. Most of the fuel's in the wings. So with the fuel imbalance, he shifted fuel to the leak, which is exactly the wrong thing to do. And if he followed the right checklist, he wouldn't have did that. And I like to talk about explosive decompressions because there's numerous interesting engineering issues that de Havilland Comet invented the problem in the 1950s. They were flying, this is the first commercial jet plane, passenger plane. If you ever look at anything historical about the Boeing 707, they'll say it's the first successful passenger jet. This is the first unsuccessful passenger jet. So they're flying 50% higher, or they had more internal pressure because they were flying higher. So the design pressure is 8.25, which is about the same as today. And they also had engines mounted in the wings, which is kind of, this is the last of that version of plane. All planes before then had engines mounted in the wing, and Boeing for Air Force bomber invented the pod mounted engines. So anyhow, with 50% more internal pressure, takeoff landing pressure cycles is most definitely an issue, but they didn't really understand all the ins and outs of fatigue design. And they believed that if they designed to twice the design pressure, they can ignore fatigue. And that is a valid engineering approach if you understand exactly what the fatigue is. Twice didn't work. Maybe this would work if you raised it high enough, but take a rather sophisticated fatigue analysis to figure out how high. But anyhow, they had multiple stress risers. They had rivets. Well, first of all, this is the first and only squarish window. They've never did that before or after. So you got this cutout with more sharper corners than ever used before, and you got rivets very close to the edge of the cutout. And I like to compare this to, this is a photo of the Titanic, where back then riveting was a standard construction method for ships. It got displaced in World War II. That was considered a big breakthrough in cost and production time, but because rivets or welding degrades fatigue life, they never really got rid of rivets, even today, except for maybe the composite planes, which are glued. So they're still using 19th century technology on airplanes because of fatigue life. They did, in fact, think of fatigue a little bit. In fact, they took a test section of fuselage and cycled it 1,800 times. 18,000 times, which actually delayed them from figuring out what happened, because that they said, oh, obviously not fatigue because we overcycled the test section. The first failure fell out of the sky at a little over 1,200 cycles, then had another one at 900 cycles. So it's like, what the heck? And the problem was, before they did the metal fatigue cycling, they proof tested to the twice the 8.25, they proof tested to 16.5 PSI, which set up compressive residual stresses and completely invalidated the 18,000 cycle test. So if they would have proof tested the production planes, the 18,000 would be valid, but they didn't and it wasn't. So this is the first time they invented fatigue testing of the entire airplane. So they built a water tank around the fuselage to pressurize it with water because they were afraid of the energy in compressed air, which is dangerous. And we're going to talk about a few examples shortly. And they'd use hydraulic actuators to mimic flexing of the wings and lift. So they just cycled this thing till it broke. And in fact, because of the increased air, I think I estimated there's like, because of the compressibility of air, there's like 20,000 times more energy in compressed air to 8.5 PSI compared to compressed water. And because of this fear of the energy of compressed air, Boeing actually fatigue tested the 707 and the 727 in water tanks. After that time, they were confident enough to do air pressure testing, air fatigue testing. But even today, if they proof test a section of fuselage, it's standard safety procedure to evacuate the building. So here's this crack with the de Havilland water testing after just 3,000 cycles. And if it was pressurized with air, basically the crack tip depressurizes because of the pressure pulse in water travels significantly faster than in air. If this had been a air pressure, the plane would have completely fragmented. The crack would run till it fragmented the plane. In fact, some of those de Havilland Comet disasters, they're talking to the pilot and he's cut off in mid-sentence. That's how fast it's happened. It's exactly like sticking a pin in a balloon. And I guess I explained that. So Boeing's innovation to address this problem was add tear straps, which they added to the 707 and they've been using ever since. So the tear strap is just a Band-Aid that reinforces against the circumferential stresses. So the crack is supposed to propagate to the tear straps and turn the corner and the whole thing opens and blows out all the pressurized air and acts like a safety valve. So it's standard design procedure. A plane is safe to fly with a 40-inch fatigue crack. That's not only based on fatigue cycling, that's also reflects the largest damage they can imagine from uncontained engine fragment tearing through the fuselage. So the rule is you can't fly with any fatigue cracks, but it's supposed to be safe with 40 inches. And in 2009, Southwest has fined millions for flying with fatigue cracks 2, 3, 4 inches long. I actually found a DC-9 that had a 39-inch fatigue crack in it. No one knew it was there until they tore the plane apart for its serious D-check maintenance, where basically they strip off all the paint, take off all the upholstery, and do a detailed inspection for metal fatigue. Which brings me to this 1988 disaster, 737 had a 14 by 18 foot blast hole, another example of explosive decompression, which also says something about the survivability of bombed planes. And nearly half the planes bombed in flight managed to safely land. Although this is obviously outside of any rational design methodology, but modern methods perhaps allowed it to hang together a little bit. So A lot of bombings have failed. I assume the modern terrorist is going to have engineers on his staff. So I'm not sure that's a trend we can count on. So everybody survived this disaster, except for one unfortunate flight attendant standing near the blast hole. Everybody else had their seatbelts on. There were popped eardrums, concussions, broken arms, stuff like that, but all things considered, relatively minor. And what was going on with this airline? They were flying short hops among the Hawaiian Islands. They're accumulating cycles much faster than all other 737s around the world. And they accused Boeing of not keeping track of how their planes are being used. So everybody was inspecting based on calendar time, and it worked because everyone was more or less flying the same. But these guys were accumulating faster cycles, so they should have their inspections judged based on takeoff landing cycles, and Boeing should have caught it and pointed it out. And they knew they had a problem. Boeing already put out an advisory to do additional inspections. So they had two reasons to do more inspections, because of additional cycles and because Boeing told them to. So the whole thing was totally preventable. But well, here we are, and it triggered a rather significant national design effort and some changes in rules. But Boeing already reinforced those lap joints before the accident. So this is on the first 291 737s. This is on the rest of them. What are we up to? Like, I don't know, 12, 14,000 by now. And this is one of the early 737s in the Seattle Museum of Flight. You can see all these external patches. Here's one, here's one, here's another one. I don't know if you can see this one. It's pretty amazing how there's just patches all over this plane. So why didn't the flap form? Well, they had a glue joint, which actually is superior because there's no less concentration of the rivet holes, but the glue alone was supposed to support the pressure, but they also used rivets. They had a redundant design, but the glue failed and didn't get caught in their cyclic testing during design because of the surface corrosion of flying over the Pacific Ocean for years. And basically, they discovered they had to totally rethink how you design for metal fatigue, because what happened was you had micro cracks on the rivet holes all lined up, which totally invalidated the standard fatigue design methodology. So this triggered a national research effort, and they changed design methods, design rules. And in 1998, they started full-scale fatigue tests, which is now mandated for all new planes. They were sort of doing that, it's just now codified. And this is the ribbing on a 737 to scale. There's extensive longitudinal and circumferential ribs, and has nothing to do with pressure containment. The reason the ribbing is there, and here's a 737 with all the upholstery removed, is if there's an engine out, you have a massive torque on the fuselage and plane that has to be reacted on with the rudder. So the fuselage is only 36 thousandths of an inch thick. Sometimes I demonstrate the problem with a rolled up sheet of paper, and it crushes in compression on the bending compression side. So it'll buckle in compression because of the big moment. So the longitudinal ribs are there to reinforce against buckling when you have an engine out situation. And the longitudinal ribs, they're pretty thin too. They'll also buckle. So the circumferential ribs are there every 20 inches to reinforce the longitudinal ribs. And they'll reduce pressure stresses, but only within an inch or two of the circumferential ribs. What I'm trying to show here, this is when they had, this is the Havilland Comet with engines mounted close to the fuselage. The tail's a lot shorter because if engines go out, the moment arm between engine thrust and fuselage center line is a lot smaller than a modern plane. As they put the engines out further and further, they needed a much bigger tail to react against the engine out scenario. And actually, the design is more efficient as you move the engine out further, because the weight of the engines counteract the bending stress of the lift. So it reduces the bending stress from lift. Of course, there's limits on everything. As you put the engines out further and further, you got diminishing structure. So eventually you need additional structure to reinforce that situation. All planes will fall out of the sky from metal fatigue if you cycle them significantly beyond their design life. It's considered a solved engineering problem. It's not supposed to happen. It still happens a little bit. You need human error. There's been a couple recent flaps forming that I'll talk a little bit about. Well, here's one example of a flap forming. So the flap formed like it's designed to. And human error, I think in this case, Boeing, they changed where they mounted an external antenna, and they didn't do a detailed finite element analysis on that. So that was a design error. Usually it's an inspection error or manufacturing error, but you need a human error to screw up and crash the plane from metal fatigue, even though they're all designed to fall out of the sky eventually if you keep cycling them. And here's some other decompression accidents. This plane broke up into 4 pieces at altitude of 30,000 feet or whatever. And it was a tail strike 22 years earlier. They put a 120-inch by 22-inch patch and buried a scratch which sat there for 22 years growing a fatigue crack. And again, once it reaches critical size, which all we know is something bigger than 40 inches, because they're not really testing to find failure. They're trying to, all testing is to verify safe design, not to find out when things actually fail, which is considerably more complicated. But anyhow, the maintenance manuals have all kinds of rules on what you can repair, what you can't repair. And if it's not allowed in the maintenance books, you're supposed to go to Boeing and get an engineered repair. So this one was clearly outside what the mechanics books permitted, and there was no record of them having sought instructions from Boeing. And also at that time, there were no rules, damage tolerance, fracture mechanics rules applied to repairs. So since then, they now have to do damage tolerant fracture design or repairs. That probably would have caught this problem. And this is an uncontained engine failure on a DC-10, and a piece, you can see shrapnel damage of the fuselage, a piece knocked out the window, and a passenger got sucked out and he lost over the ocean. These are supposed to be old stories and not supposed to happen today, but one just happened in the Southwest Airline in 2018. And this case, windscreen was sucked out at like 18,000 feet because the mechanic the night before, he eyeballed the screws and put in underside screws. So the pilot got sucked out, but he got his feet caught in the control column. And according to the TV version, which I've kind of come to wonder about, because I often end up correcting TV versions of these incidents and accidents, 2 flight attendants wrestled his legs out of the control column, and they kind of stood there holding them, trying to figure out how to get him back in the plane. And one flight attendant said to the other one, "I can't hold him any longer. Can you?" "No, I can't either. Should we let him go?" "Yeah, let's let him go." And the co-pilot said, "No, don't let him go. He'll get sucked in the tail engine. We'll have even more problems." And this is an improperly latched cargo door on a 747. If you blow out pressure in the cargo hold, the floor will collapse. In fact, DC-10 was lost in the 70s that way. the structural damage wasn't that bad, but it broke some control cables run into the tail section. So the pilots lost control and everyone died. And since then, they mandated blowout panels in the floorboards, which probably saved this plane. But because of structural damage in the floor, still 9 passengers were swept out of the plane. And here's a view from the inside. They decided the problem was bad wiring, but the ground crew kind of forced the door shut. He should have noticed it wasn't properly latched. And the blowout panels were activated. So the exact opposite of decompression is hypoxia, which happened on a Boeing 737 in 2005 in Greece. Everyone passed out and the plane flew on autopilot. This is the actual plane. Everyone's passed out there. The Greek Air Force is buzzing the plane, trying to figure out if they can make any sense out of the situation. The answer is no. And there's a switch on the ventilation system. This part of my screen is blocked out. I can't read this because there's this AIAA logo here. Well, anyhow, there's 3 settings on this switch. This is an old analog 737. The digital ones don't have this problem. But there's 3 settings on the switch that controls the ventilation system. It's on, off, and alternate for an alternate source. So it's always supposed to be on. It's always on. The only reason to turn it off is if the mechanic is doing maintenance on the system. So he shut it off and failed to turn it back on. And they faulted Boeing for being ambiguous with the checklist for the mechanic. It said, restore the control panel to its original settings. It did not specifically call out the switch. And the pilots didn't notice it. Although they're looking in the sunlight. And the other problem is there's a Cypriot pilot and a Greek co-pilot trying to debug the wrong problem in their non-native English while they're becoming hypoxic. So I talked to 2 737 pilots about this switch, and I seem to know more about the switch than they did. I couldn't believe it. I wondered what the heck's going on here. Did I manage to find the world's 2 dumbest 737 pilots? And I figured, no, they don't let stupid people fly these planes. But then it reminded me, one time I got to spend an entire week on an aircraft carrier. There's me staring the aircraft carrier. So everywhere I turned, my head was spinning with engineering questions. Finally, my host said, stop bugging us with engineering questions. Our job is to follow the procedures. So engineers write procedures, mechanics and pilots follow them, and sometimes bad things happen. And incidentally, most everyone in the aviation community is willing to dismiss the missing plane as a criminal act. Certainly hypoxia could explain lack of communication, but a hypoxic crew does not steer the plane repeatedly. There are minor course corrections as if someone was joyriding. And you can also explain what happened with a fire. Well, if a plane's on fire, the first thing they say is, we're on fire, find me a landing immediately. And even if they're going in the ocean, it's like, we're going down, come and get us. So it's a criminal act. The problem was the investigators will not say anything in the absence of hard, concrete facts. So with the investigators not saying anything, everyone's mind is running with all kinds of wacko conspiracy theories. It is some kind of criminal act, period. And I looked at crash testing, which was interesting. You can actually break up vertical versus horizontal crash testing. The structure and the humans both respond differently. So it makes engineering sense to test separately for vertical crashing versus horizontal crashing. There's only been 3 full-scale crash tests of large commercial planes. Two of them were in the 60s, and one of them they had a total lack of breakdown of all their instrumentation. They recorded zero data. There is one from the 80s we'll talk about shortly. It's more common to do a drop test. They'll take a section of a fuselage and drop it and take all kinds of recordings. So ejecting up is the same as crashing down. Both will compress the spine. And this is an actual photo of a Air Force pilot during a show. He's not over the crowd like it looks here. It's just a funny angle. Everything's safe. Everyone lived, including the pilot. He ejected 140 feet off the ground, and he shrinks 2 inches. He's in the hospital for observation. His wife shows up. He gets up to hug her, and she's taller than she's supposed to be. So the Air Force, there's an altimeter air setting. So this is a dramatic opening at an air show. The very first event, the pilot climbs straight up and then goes into a dive straight down. And his recorded altitude was wrong, faster than he can make any sense out of that. He was able to fortunately sense there's something wrong, and he's getting closer to the ground than he's supposed to. So he safely ejected just 140 feet off the ground. So the Air Force studied this, and they concluded 7% of Air Force ejections result in spine fractures. And it's not only the acceleration of the ejection seat, which is a design number, but if the plane's trying to pull out of a dive, it's pulling acceleration too. That adds to the acceleration ejection seat. So that's kind of a random number. So the two of them could exceed the human's capacity. Of course, you test humans, it's not like testing pieces of steel. You have tremendous statistical scatter. So the Germans studied this extensively during World War II when they started getting in their high performance fighters. If you don't eject fast enough, the vertical stabilizer will cut you in half. So you have to eject faster than the tail section can sweep through your body. So they destructively tested people and concluded 25 Gs will crush your spine, which is about 1,500 pounds on a load cell, which is still an FAA mandated number. They do crash testing of seats, and the load cell in the crash dummy spine cannot exceed 1,500 pounds. It's a lot easier to crash test a seat as opposed to an entire plane. So this is the most studied instrumented photograph crash in history. It's a test crash done in 1994. They were testing a fuel additive that gels the fuel to prevent misting during impact to reduce post-crash fire. And it failed miserably. What happened, the gel worked, it's just that the design crash was to slide through steel barriers that ripped the fuel tanks, but instead they were off a bit and they ripped into the engines. So the fuel was gelled and wouldn't miss, but it still will burn. So leaking fuel directly on the hot engine parts, and you had a terrible fire, and we have a video of this. So somehow the FAA estimated 19 of 52 simulated passengers would survive the fireball. Don't ask me how. So they're only impacting at 17 feet per second vertical, which we'll look at some of the design numbers about vertical impact. So how the crash dummy survived the fire, don't ask me, although I guess it's not directly on the fuselage. Presumably, I'm pretty sure they had fire trucks standing nearby, maybe a couple miles away, simulating the situation of rather quick response of fire equipment with some delay of a few minutes. So this is the drop test they did for this test crash. They dropped a section of fuselage just 6.2 feet with an impact of 20 feet per second. And want to compare that to a more recent drop test of a composite 787. The FAA told Boeing, prove it's as crash worthy as an aluminum structure, but they didn't tell Boeing how to do that. It basically said, submit something and convince us it's as crash worthy as aluminum. So they chose to do that by doing a drop test, which they dropped from 15 feet with an impact of 30 feet per second. And it passed. And one of the things got to pass is a load cell in the crash dummy spine. And this is the drop test after 6.2 feet drop. There's very little damage because this is one of the more rigid sections of the fuselage. This is where the wing box, where the wings connect to the fuselage at the wing box. So there's lots of structural reinforcing to support all that wing load. And because it's so strong and not crushing, absorbing energy, 40 to 60 Gs shot straight into the dummy spine. So that very little damage would have killed all the passengers. And this is highly developed by now. It took them decades to figure out how to design everything to respond like something like a human. And this was first mandated in the 60s when they started looking at seat belts. The Fed said, thou shalt have seat belts and prove they work. So again, nobody really knew what that meant. And the automotive companies started on this journey that picked up in the aviation business somewhere along the way. So the government mandates testing of literally an entire family, kids, infants, male, female. There's only one standard crash test dummy for the crash seat for planes. So it's still hard to get something that mimics a human, but there's a big advance in the computerization structural design. Now that you got a machine that everyone agrees to is adequate for design purposes, you have the repeatability of a machine. They did a lot of cadaver tests to prove these crash test dummies work. In fact, they were still doing that last time I looked, although it's been a few years since I've been following this. And for example, one of the requirements is they'll embed a load cell in the crash dummy's head and drop it just 10 inches on the very rigid block of steel. And the spec is it's got to record 210 to 260 Gs. So that's one heck of an impact. Of course, that's not the way things impact in cars or planes. So we can look at some of the design parameters for vertical impact. Boeing did a survey and decided pilots think they had a hard landing at about 4 feet per second, which means the pilots say, Mr. Mechanic, I hit kind of hard, why don't you take a look at everything? The design limit on the landing gear protecting the plane is just 10 feet per second, which is a drop of just a foot and a third. It's not 18 inches. It's not much anything. Now there's a crushable element in the landing gear that will absorb a little bit more energy. So there's no expected plane damage up to 12 feet per second. And fatalities expected greater than 25 feet per second and greater. But this is based on surveys in the 80s. So hopefully newer planes are better. And I think this Boeing 787 test is an indication of that. And we'll talk about another example crash. Now, there's couple of issues here. You can always have a severe post-crash fire and kill a lot of people with a modest crash. So they're kind of two separate things. Of course, the harder you hit, the more likely you are to have a post-crash fire. And above some point, if you hit hard, you have hard enough impact to spray the fuel, you're igniting a fireball. But in terms of fireworthiness, everything's gotten a lot better, significantly better. But there's still no solution to a high impact fuel spray igniting a fireball. That miracle crash I talked about in the Everglades, we had the significant fragmentation of the plane. That was 37 feet per second vertical impact. And here's the expectations based on these surveys of planes in the 80s of 100% fatalities. Which brings us to this Boeing 777 crash in London in 2008. The approach is mostly a glide, but at the very end, with all the stuff hanging down, with the landing gear extended and the flaps extended, you got significant drag. So they typically increase the throttle and thrust at the very end. They're gliding all the way down until the very end. Well, these guys hit advance the throttle at the very end and nothing happened. So they lost thrust at 720 feet and they're going just 108 knots at 200 feet. There's no estimate of when they stalled. Now, they didn't drop out of the sky. If they drop they're stalling somewhere around here, but they don't really know, which I'll explain momentarily. So they didn't drop out. If they dropped out of a sky like a rock, they would have killed everyone. They'd crush everybody's spine. So there's significant lift. It's just not a lift for a normal, correct, safe landing. So the stall speed was not identified in the study. They'll do simulations of flights in the simulator, but the simulator is totally based on test flights. It's unsafe to stall that close to the ground, especially with all that stuff extending. So no one really knows, and the CFD cannot add anything. So the CFD cannot model upsets or stalling. Plane gets out of position just a little bit, falls out of sky, kills 300 people. CFD has absolutely nothing to add. It's so far off, they don't even study it that way. I don't know about you, but I'm pretty skeptical about extremely complicated computer simulations. Actually, the story gets a little worse. About 7 years ago, the FAA mandated a simulated upgrade, the simulators to fly deeper into stall. And that would be a very massive engineering update. They'd have to solve this problem, and they gave them 5 years to do it. And the deadline passed and nothing happened. Everyone gave up on. I don't know the actual story, but I'm going to call that another CFD failure. Boeing had a couple of test pilots that stalled the 737 over 700 times in support of this anticipated requirement that never happened. And NASA said they could simulate a plane with CFD supplemented with wind tunnel tests. But you'd have to do it for every model plane. Even a 737, there's quite a few of them with different configurations and different dimensions. So why did this one stall, this 777 in London stall? Of all things, is fuel line freeze up, which is a unique problem. So they redesigned this shell and tube heat exchanger. So this was 25 feet per second vertical impact. Now, you got the landing gear extended, and they'll absorb some of that energy, but remember it's kinetic energy, velocity squared. So if the landing gear was good up to 12 feet per second, maybe it absorbed a quarter. And they had a reading at 2.9 Gs, but that's kind of a funny number because to capture the maximum G load impact, you'd have to have accelerometers in many, many locations. I'm going to talk about Dutch roll again. It's historically interesting in two recent examples. Am I okay on time here?
Yes, you have time till around 11:40
okay.
Pacific time.
Well, Boeing had designed the first swept wing bomber, and it would not fly straight. It was unstable. And they solved the problem with the yaw damper, which was very controversial at the time among Boeing and Air Force engineers, because a lot of people thought the plane should be stable without a mechanical device that could break. But they couldn't solve the problem. Subsequent designs had less and less of this Dutch roll tendency, and it's totally designed out. You still have a yaw damper, but it's there for passenger comfort, not to solve Dutch roll. So there's this coupling between yawing and rolling. And the real problem is, this is a problem much more of swept wing planes. As if you yaw too much, you have this massive unbalance of lift, which causes a severe roll, enough to lose control. So this is the B-47. The thing was just, it was amplifying till something bad happened. Today they've designed it out, but it was a problem in the early 707s and a bit in the 727. By the time they got to 737, it's solved. So this is the Boeing 707 in 1959. It's similar to the bomber B-47. And they're doing Dutch roll recovery training. Now, this is back in the late 50s. It's kind of a strange situation. They were killing more pilots training these oddball situations that never occurred during passenger flights. And finally, it was a serious problem, but everything got better, including the simulations got better to the point where there's very few flight training. Well, I don't think they do any accident scenario training in the air. So anyhow, they're doing Dutch roll recovery training of line pilots, and it rolled so violently, they threw 3 engines and they crashed. And I think they killed 5 of 7 flight crew, 1 or 2 survived. And after that, Tex Johnson, the famous Boeing test pilot, he recommended design changes. In the book he wrote, he said, don't yaw more than 15 degrees. So they added a ventral fin and they made the tail a little taller to resist this yawing motion. And that helped a lot, but it was still a problem, a diminished problem. So if a bigger tail suppresses Dutch roll, perhaps a smaller tail can create Dutch roll. And we have a modern Airbus example of that. This Airbus 310 in 2005 had a composite rudder break completely off because of a manufacturing defect. So that reduced the yaw resistance enough to induce a Dutch roll. But as they descended into denser air, it damped itself out and the plane landed safely. And in 2013, a tail fell off of a Air Force tanker, which is a modified 707. And basically the yaw damper broke, there was a Dutch roll, and the pilot didn't have sufficient training to recover from it. You're supposed to recover with the wings, not with the rudder. You try to steer the plane with the rudder when the plane's yawing, you can exceed the structural loads on the plane and break the tail off, which is what happened here. So a plane is not designed to fly sideways. If you yaw too much, you yaw to the left and simultaneously swing your rudder all the way to the right, you're putting more load on the tail section than it's designed for, and it'll break off, which happened here. So that plane crashed and killed the crew. And this Airbus crashed in 2001, shortly after takeoff from New York City, just a month after 9/11. And this wasn't Dutch roll, but the pilot oversteered the plane and broke off the tail section. So we got the same situation. He was flying behind a plane in front of him, I think a 747. So the plane was being jostled from wake turbulence. That was not the problem. The wake turbulence was not a problem of structural strength or flight stability, but the pilot was responding to increase passenger comfort. And he was swinging the rudder back and forth pretty much as fast as he could do it. And basically, every time he swung the rudder, it would yaw, and the yaw was kind of overshoot before it stabilized, and he created this combination of excess yaw and excess rudder. And it also was an engineering failure of sorts. The engineers said, we designed the plane for how it's meant to be flown. You're not supposed to do that. And the pilot said, you mean to tell me we can break the plane structurally? I thought it was designed so no matter what we did, we couldn't break the plane. And the flight manuals did not specifically call out, don't swing the rudder back and forth as fast as you can. They do now, but they didn't in that model of that plane. So that was another disconnect that crashed the plane. So this possibility was sitting there, I think, for like 15 years before all the combinations came together. It's considered a bit of a cowboy maneuver. It was not a standard pilot maneuver, and most pilots wouldn't have tried it. So you had to have the right combination of circumstances. Also, this rudder in this specific model was sensitive. You could swing the rudder back and forth with much less pedal pressure in the cockpit. So it was a unique combination, just sat there till everything came together and crashed the plane. So this is the first and only example of a composite structural failure. We broke off the vertical stabilizer. And I'm trying to show 150 plies of carbon graphite reinforced epoxy in the attachment rear lugs. The carbon fiber is only 2/10,000ths of an inch thick, which would be 15 to 30 human hairs, or 15 to 30 times finer than a human hair, depending on whether it's Swedish or Italian. May all your decompressions be slow. It's an old Irish toast. Are any questions? Any questions? Hello?
Hello, can you hear me? I think the internet speed is kind of, bandwidth is kind of.
You're breaking up a bit.
Seems to be okay now.
Should we try questions now?
Oh, okay. All right, so everyone, so Professor, your presentation is really wonderful. Really appreciate. So prior to everyone, I think the chat room somehow was disabled. So if any question, please type in the Q&A or raise your hand, we'll unmute you. So pretty much we'll do the unmute. So it's better you can interact with the professor directly. So I saw two persons raise hands. So Victor, go ahead. You can unmute yourself.
Oh, okay. Can you hear me?
Yes, yes.
I can hear you.
Okay, yeah. So how much have you worked with the NTSB on some of your on your research? Did you had quite a bit of work with the NTSB?
No, I get asked that a bit. It's like people ask me, ever been in an airplane crash investigation? It's a really big deal. It'd be like inviting myself to a murder investigation. But I certainly studied their reports a lot. Looked at a lot of engineering reports and FAA safety reports. There's also a public docket for the more recent crashes that has significantly more information that nobody seems to find ever.
Okay.
I've had more work with AIAA. I've given over 30 talks.
Okay, so Victor, if you have more questions, you can welcome to come back. So next, Mitch, Dr. Info from JPL. So please speak out.
Yeah, hi, can you all hear me?
Yes.
Okay. I may have missed this, but and if I did, I apologize. But one crash I didn't hear you mention. Sorry if you did. Was the Concorde crash? Did you address that one? And I'm curious if you have any sort of comments on that particular.
Well, no, I didn't address it in my talk or in my books. I didn't study it. It's kind of an oddball crash because they had a tire failure and a big hunk of rubber smacked the fuel tank and set off a pressure wave that ruptured the fuel tank. So that's really an oddball circumstance that can't happen in any other plane. My second book, I did look at a lot of tire wheel failures and takeoffs.
Okay, thanks.
Well, welcome to speak out.
You say Kyle?
Yeah, Mr. Sweeney.
Yes, thank you. I had actually two questions now. For one was for the Malaysia airline crash. What was the official conclusion according to the crash? Like, I appreciate your opinion, like your input on that crash. I was just wanting to see more detail about it.
Well, I wrote more about it in my second book, but no, there was no official conclusion. They really won't until they recover the black box, and I don't think they will. People don't understand how big the ocean is. It's like trying to find your wedding ring in New York City with a pen light. I mean, if the guy set out to be lost, I don't think it's that hard to do. Total criminal activity, I think the aviation world accepts it as that.
Okay. Yeah, and then my other question was like, as far as all the crashes that you have talked about, was it usually due to human error or a combination with the engineering errors as well?
Well, depending on which bit of data set you grab, the rule of thumb is pilot error is like 50 to 75%. I shied away from that, although my second book, I had that co-author pilot, did a little more with it, but I'm kind of focused on engineering insight and interesting stories. And so I'm not a pilot. I'm hesitant to get into piloting issues. Maybe I'll directly quote NTSB reports, but I shouldn't be interpreting pilot. Those big planes are incredibly complicated. It's amazing.
Mm-hmm. Yeah, I was really interested in that talk. Yeah, thank you.
You're welcome.
Okay, Ed, Mr. Story.
Just a quick question as to how quickly do you see the engineering problems decreasing over the periods that you've appeared to study, which is perhaps the late 40s to the present? Are they rapidly approaching design issues of only 10% or 5%, or how would you calculate, or how would you describe the reduction in engineering issues?
Well, they're about 50 times safer than the beginning of the jet age, which would be, and I'm talking about the commercial jets in the late 50s, early 60s. They're so safe now. I don't see them getting safer that easily, and it's kind of diminishing returns. Everyone's expecting a computer to take over everything. I'm not a big fan of computers doing everything. My favorite example, imagine if a truck wanders onto the runway at the worst time during takeoff. It's the technology to solve that problem, to gauge the distance and make the decision to alter the thrust or slam on the brakes. How long has that been around? I don't think they'll never do it. The reason they'll never do it is they do a cost benefit analysis, which is nobody knows it's occurring. It's almost done secret. It involves putting a price on a human life and trying to estimate how many lives are saved by the new safety. The cost of the new safety is just an engineering study, but then they got to estimate the cost of the improvement, which is lives saved and reduced injuries. Well, if you do that, you do a cost benefit analysis of something that almost never happens, that being a truck being on the runway at the worst time of takeoff, you'll conclude you can justify spending almost $0 to solve that problem. I think there's probably 100 little things that almost never happen. I don't think it's easy to take the pilot out of the loop. And that specific problem, again, if when it does happen, they go nuts pounding on the driver of the truck. They're not going to redesign the plane safety features.
So if I may ask one follow-up question, which is unrelated to the first one, are you looking carefully at the certification processes that are being used for EVTOLs and other type of urban air mobility or advanced air mobility type vehicles that are under construction or under experimental use today?
No, I'm studying as an educator, so I'm looking for. Well, first of all, well, you guys understand how complicated this is. You're all engineers. It really is rocket science. The size of the book of things I don't understand is only about 10 billion pages long. So my focus is trying to find interesting stories that have engineering insight that I can explain correctly and have confidence I know what I'm talking about. So I'm not in the safety loop designing safety systems. I'm looking for interesting stories to talk
So Ed, any further question?
Well, I'd just add one item from having read accident reports quite a bit, nowhere near as much as I'm sure you did, sir, but on that flight that was coming into San Francisco, I've forgotten the flight number and so forth with the Korean Air situation. I think there was some question, and perhaps you've dealt with this in one of your books, but I think there was some question as to whether the Czech pilot, who had tremendous experience in this, was dealing with a Korean cultural issue, which was don't correct the left seat, don't correct the pilot in command, especially when it has to happen so quickly and at the last moment or two. Was that a factor in your thinking or your writing?
I think it was mentioned as a factor, but I don't think it was considered an overwhelming factor because it turns out there's a long flight, so there's extra pilots on board, and there's a third pilot sitting in the cockpit actually calling out sink rates, saying you're sinking too fast. So they thought the auto throttle was on and it wasn't. Now, that's how I explain it in a soundbite. My pilot co-author is a bit furious with that. He thinks it blames the pilot too much, and he went into an involved discussion of the computer systems, and it's complicated. I mean, flying a small plane, you only got 3 controls, rudders, elevators, and thrust. But these things, I got the pilot to agree there's 3 ways to fly the plane: 100% auto, 100% manual, which are simple to understand. The third way, which is my jargon, but the professional pilot agreed with it, is multiple software selections. So they're flipping through the computer screens, making selections that do multiple things at a time. All the basic functions are still there, but that damn computer and the multiple systems is complicated. That's one reason why I don't want to deal with the 737 MAX. It's all proprietary software, which I don't think is publicly available. And it's piloting issues that have to be interpreted by a pilot. I don't know if I answered your question or 6 other questions.
Oh, that's fine.
Okay, Ed, if you have more questions, you're welcome to ask shortly later. So the next one is Daniel, Mr. Scully. Welcome to speak up. I think he might have left. Let me see. Okay, so his question is, may you expand upon the APA Advanced Accident Investigation course you took?
Well, University of North Dakota is one of the major flight schools in the country now, that and Embry-Riddle. And so they talked Airline Pilots Associations into having a 3-day crash seminar at UND, and I talked my way into sitting in on this paid training seminar, which is kind of cool. I got to hang out with big plane pilots for 3 days. But the focus of that training is if they're called to participate in an NTSB investigation, this is what's going on and this is how you should behave. So that really wasn't crash investigation per se, although they certainly talked about crashes, but it was a training seminar for pilots in case they got called into it.
Great. I think that your book, Professor book and course, very interesting. If you can forward, the information, we can, share with our people here.
Okay, it's on
thank you.
Amazon. In fact, quite a bit of the book is online in Google Books and Amazon. I don't know.
Yeah, that would be great. If you can share with us, people would love to enjoy and learn more and look up your course information. So the next one is by Mr. Randall Ushiyama. Do you want to speak out, Randall? You can unmute yourself. Well, if not, I'll read the question for you. Randall asks, have there been any crashes due to electronic failure, computer failure, other than the MAX? How hard is it to determine electronic or computer failure?
Well, computer failure is subject to interpretation. And my interpretation of it, you can't blame the computer unless the computer did something directly caused the crash. And I'm not aware of that occurring. But there's crashes where the computer caused confusion that's in the loop. My favorite example of that is Air France 447 crashed in the Atlantic. I sometimes talk a lot about that one, but I didn't today.
Yeah, Professor, I wish you can speak with
let me
us
mention a
next
couple
time.
things. Let me mention a couple things about that flight. So Airbus and Boeing have totally different philosophies on flight safety. For example, you cannot stall an Airbus plane. The computer will not let the pilot do something that will stall it. And Boeing's philosophy is the pilot should always be in control. But so they have, like, for example, a stick shaker, which is in the history of flying. When you start to stall, the turbulent air shakes the tail section so much you can feel it in the controls. So Boeing artificially introduces that when the plane's in trouble. Airbus doesn't do that because they think it's impossible to stall the plane. Well, this plane stalled. Well, it shut off. Autopilot shut off because the pitot tubes froze. Worse still, they were freezing and unfreezing. So they had valid and invalid airspeeds, and a stall alarm was going on and off intermittently. And all they had to do was maintain straight and level flight, and they couldn't do it. They got out of position, crashed the plane. There are other contributing factors they couldn't see, and they did a study, the Army Air Corps in 1932, that experienced pilots could not fly straight and level without seeing the horizon. So they invented the artificial horizon. And all they had to do was use the artificial horizon. They had enough information to fly the plane straight and level. But I think it was, they didn't trust the computer. The official report says there's no explanation why they couldn't fly the plane straight and level. So my explanation is that computer confusion made them not trust anything. They got out of position, and there's no way to recover. That's not part of the design or training or anything. And CFD has nothing to add. I guess I'm done with that question.
If I could just add a quick portion of that, as I understand it, and perhaps you were just dealing with this, Professor, but on the Airbus design, the the right control stick doesn't respond to the left control stick. And the left seat was the third pilot on Air France 447. He was the least trained. He thought he was going down. He kept pulling back. The guy in the right seat didn't know that was happening. They got up to whatever the number was, 45,000 feet or something like that in Coffin Corner and started to stall. And by the time the captain, who had been sleeping, he was supposed to be sleeping, came forward, they were falling at 10,000 feet per minute and there was no time to recover.
Yes, well, the captain came in the middle of it. I think it was like 4.5 minutes from when the autopilot shut off with an alarm to total fragmentation in the ocean. The pilot got in a minute and a half. He had enough time to do something. Of course, he's walking in the middle of a crisis. He actually applied the speed brakes, which suggests he thought they were having a high-speed stall. So all three of them were totally confused. All they had to do was maintain straight level flight, follow the horizontal horizon. There's another trick I like to point out. Well, it's a dark and stormy night. They're totally disoriented. You can't walk a straight line blindfolded. Moving in 3D space is more complicated. And it's actually simple physics. I usually explain this with a couple of simple diagrams. When you turn a plane, the inertial forces of turning go right through your spine. There's no sideways shove. You cannot feel you're turning. Unlike a car, you turn a plane, you're shoved into the door. You turn a car, you're shoved in the door. So I think that's kind of an interesting physical connection to these upsets. You cannot feel turning the plane, so that adds to the disorientation.
Okay, next question is by Mr. John Chapman. John, go.
Yes, sir. The question is engineering failures are in many ways similar to battle damage, military battle damage. Have you taken any look at some of the survivability improvements that the military has developed, such as the famous Israeli F-15 wing loss, and he still brought it home?
Well, you got to understand, like a fighter plane is a Indy 500 Formula One race car. Passenger plane is a school bus. They're just totally different designs. The design G loads on a passenger plane are 2.5. On a military plane, it's a secret, but it might be like 8 or 9 Gs. So they're very plus all the military crash reports are unavailable, as they should be, because it gets into performance issues.
I agree with you. Real-time data is very hard to get, but sometimes there are surprisingly similar sorts of things. For example, C-17s have been seriously damaged and still managed to recover unassisted. In some cases, they've been modified on the ground and brought them home. There's lots of different things that are related, you might say.
Well, yes, but there's no military crash reports publicly available to be studied.
Thank you.
Okay, Byron, you have any question? Do you want to speak out? No, looks like it is. How about Victor? You raised hand. Do you have another question?
Oh, no, I didn't. In fact, that last question answered one I had up there. Was it any, what research you do, military accidents and stuff? And, you know, they had a lot of military accidents in the Air Force. And you said it was unavailable. Those are reports or incidents are not available, or accidents not available to the public for research?
Yes.
Okay. No, I didn't have any other, that was it.
Oh, okay. So John, I saw your raised hand sign is still there. Do you have another question?
That's a negative, sorry.
Oh, sorry. All right, so any more questions from everyone? It's a great opportunity.
I wanted to ask you one more. You said you got your training from Amarillo Aeronautical University?
No, I'm at the University of North Dakota. Them and Embry-Riddle have the two major flight schools. I just mentioned them as a second major flight school.
Yeah, you have to really keep. I found you have to really keep up with it. I have a minor in aircraft accident investigation, aircraft accident investigation in Riddle, through a degree I obtained from it in 2001, and it covered a lot of this information you're covering here. But yours is sort of like a personalized account, whereas we had to concentrate more on NTSB, FAA type stuff. But yeah, you have a nice refresher here. It takes a lot of reading up. I guess you got to keep up with it, because I read all the accident investigation that they have online, or not online, but on television. They have those series that come on. I watch those quite a bit. But I appreciate your time, though. This
Yeah,
was
well,
all.
small planes are totally dominated by pilot error. And for my purposes, basically, the more people they kill, the thicker the report for me to study. Everything's proprietary. It might as well all be under military lockdown. What I've done is anally researched for years, bits and pieces of information, and strung it together in a narrative, because everything's proprietary.
Yeah. They've had accidents in the Air Force, like, for instance, C-130s, the center wing box failures and stuff like that. I don't know if you've seen those. They had one aircraft, it wasn't quite military, but it was a military-used aircraft. And I think they were spraying, they was using it for a fire suppression in one of the forests. And for some reason, the wings snapped at the splice boat. The center wing, the C-130 has a center wing, and then the left and right outer wings are attached to it. And where it cracked was what they call it the attach points for the outer wings to the center wing box has separated it. Actually, I guess it was due to fatigue, but it's a ring of about maybe 25, maybe 30 bolts, big large bolts that hold it on there. For some reason, it just cracked off of there. But it wasn't detected on the ground by through analysis or inspection. It detecting the cracks. They had those type of accidents, and they lost the whole crew because the wing, once the wing split, you got two turboprops on one side, you just break away. They had a lot of accidents in the Air Force. They should release for your type of study, because and I don't know how in depth or in detail they'll let you get into that, because some of that stuff may be classified. But
If it's available, I'd look at, but I'd only look at it as a similar plane to commercial planes.
yeah, checking some of the C-130 crashes, you'll see some of those C-130s that actually have had center wing box crashes because of the separation of the rainbow fittings on the inner and center and inner wing attach points. They just, I guess, for some reason, they developed cracks and you couldn't detect them with the eye. Or actually, they had at that time, I don't think they had developed a procedure to check them. Like X-ray, and it's very hard to dive penetrate in that area. So you mostly have to do a visual inspection. And with a visual inspection, the eyes are not going to hardly ever pick up a crack in a forged part. So they've had instances, and they've had to replace the entire center wing on those aircraft. They just deemed them too old and just replaced them all as many as they could afford to. That was just one aircraft, but yours, you mentioned the crash they had from the Atlantic. There was an aircraft that was flying from the Atlantic. I can't remember which airline it was. It was flying from the Atlantic to one of the Eastern European countries, and it crashed in the Atlantic. And it was due to I think it was a PDOC tube, inoperative PDOC tube or something like that frozen up.
Yeah, that was Air France 447.
447. Okay, yeah, I was in Afghanistan when that happened, and I was wondering, did the guys, even if the PDOC tube had frozen up, they could still see outside the. I mean, the windows wasn't frozen up, but they couldn't take a relative view of the Earth. They could keep in their eye where they were, unless they were in the clouds. I don't know whether they're in the weather or not, but if you can keep your eyes out of the window and fly by the seat of your pants, for instance, per se.
Well, it was a dark and stormy night. They couldn't do that.
You couldn't do that. Okay, I was wondering what happened in that, because I didn't get the results of that. Seemed like they could have avoided that, because that was the only instrument that was off, was airspeed indicator.
Yes.
How did
That's
they
why
get?
they don't know why they couldn't fly straight and level.
So, but they couldn't fly straight and level, even though the airspeed was dropped off. So they didn't have any relative feel of the airspeed because the airspeed indicator had malfunctioned.
Well, if they kept maintained the same thrust and kept the plane straight and level, that solves the problem. That's all they needed to do.
Yeah, but I was wondering why they didn't do that, though. I mean, you have,
Well,
you have an instrument go out, you say, oh, we got instrumentation failure, or an instrument that's that's defective and stuff, but everything else is good. So you maintain your course, maintain your level. You could maintain that. I just wondered why did they get caught up in the automation or something? But they couldn't switch something off soon enough, or what? I just
well, the official explanation is they don't know. My explanation is they were overwhelmingly confused by computer issues. Well, who hasn't had a computer issue that there's no way to make any sense out of?
Yeah, I understand that.
Okay, on this, Victor, we'll have a professor coming back to talk about the airplane 447. Unfortunately, the time is up. I think Ed has another question. Ed, do you want to ask Professor?
Yeah, just a very quick one. Professor, thank you very much for a wonderful presentation. And is it possible to get your email address?
Yes. It's G-Bible, like my name, at Gmail.
gbible@gmail.com?
Yeah. And just type my name into Amazon or Google Books, and you'll see maybe half the book up there.
Fantastic. Thank you, sir.
Of course, buy them. They make great Valentine's Day gifts.
Yeah. Professor, I think the time is kind of limited, but there's, I think, anonymous attendee asked a very quick question. He was saying, is there any comments about helicopters, compression, or any comment about those things?
Well, I didn't do anything with helicopters. I was at a GE engine plant, surprised to learn it is possible to safely land with no engines, but it's a very difficult maneuver. You have to have a glide slope enough that generates enough rotation so that you have enough lift to survive it. So it's possible, but it's difficult.
Let me just quickly add, Ken, that I'm a helicopter pilot. This is Ed Story talking, and it's called an auto rotation, and it actually, you train regularly for it, and it's one is quite capable of doing it if you're recently trained on it.
Well, you just use helicopter knowledge.
I'm sorry, sir, was that a question?
No, as a statement, you just exceeded and used up and exceeded all my helicopter knowledge.